All right, we'll get going now. Welcome to the physics department. As you may know, the physics department engages in a very wide range of research. There are 45 active faculty here in these buildings. And the area that I work in particular is experimental cosmology. And as you'll see, what we're doing is trying to learn about how the universe started and evolved, but by building experiments that we really build with our own hands and that we take out and measure things. Now, here is a one-slide summary of the entire talk. So if someone tonight asked you, hey, what did you see at Cal Day today? If you can remember what's on the slide, you'll remember my entire talk. And that is, starting here, that we live in a golden age of cosmology. In every physics field, in fact, in many endeavors, often there's a real golden time for progress. And I'll argue that right now, the last really 20 years, we are really learning a huge amount about cosmology. Next here is that in that golden age that we're in, we're starting to have a detailed model that is emerging of how the universe started and how it's evolved. That model starts with a Big Bang. We find that the universe is expanding with time, getting bigger and bigger. We expected that expansion to slow down with time, but we've been surprised by the discovery that that expansion is in fact accelerating. We don't know why it's accelerating, but we are saying that is being driven by something called dark energy that we don't yet understand. We've discovered that most of the matter in the universe can't be seen. It's not in stars and the things that you see out in the sky. And so we've given that a name too, even though we don't understand it. We've called it dark matter. So this is a huge amount of progress, but we still have this minor problem that we don't understand about 95% of the stuff in the universe, and that is this dark matter and dark energy. And by 95%, I mean if you weigh how much energy there is in the universe, 95% of it is in this dark matter and dark energy that we don't understand. So let me begin at the very beginning, that the universe began with a bang. And what evidence do we have from this? Well, let's go back to 1927, where all cosmologists smoked pipes. And we'll hear about the story of Edwin Hubble, who, using this telescope here, the Mount Wilson 100-inch telescope, he started looking at this data here, which is he started measuring galaxies, asking how far away are the galaxies, and then asking, well, and how fast are those galaxies going? And we found it's very interesting that the further away the galaxy is, the faster the galaxy is going. And that is consistent with an expanding universe. Now, why is that? Why do you get that? The further away a galaxy is, the faster it's moving. Well, I should say that to talk about how fast we're learning things, it was controversial just before then that there even were galaxies, meaning that, you know, when you look out in the sky, you see the Milky Way, and you know that, now you know that that's our galaxy. You know that that's, we live in a spiral galaxy. And you know, and everyone here knows that you look outside our galaxy and there are other galaxies. But even that was controversial back in the early 1900s. So when Edwin Hubble said, hey, you know, not only are there galaxies, but when you look at how the ones that are further away are going faster, that was really a revolution in what we knew. All right, so let me get back to the question. Why should it be that the further away a galaxy is, the faster it's going in an expanding universe? And I've got my, my little toy universe here. And what it is, it's a balloon. And the galaxies are painted on this balloon. You can, you know, if your eyes are good, you can see the galaxy. And this is a 2D model of our 3D universe. So just the surface, you just think of the surface as a good model for how the universe expands. And so what I'm going to do is I'm going to blow it up for you here. Okay, now if you put yourself on any one of the little galaxies on my little balloon here, and as the balloon expands, you ask, what's happening to all the other little galaxies on the surface of that balloon? Well, what you'll find is that every single galaxy is running away from you. Okay, this one, from this point of view, every other galaxy is running away. And what you'll find is that as the balloon expands, the further away the galaxy is, the further away the dot is on the balloon, the faster it's going. Okay? So this happens. This is just 2D, but it works in 3 dimensions too. You can think of people like to talk about loaves of bread with raisins in them. And imagine you put a lot of yeast in it, and as it bakes, it gets bigger and bigger. And all the raisins similarly will run away from each other. And the further away the raisins are, the faster they'll be running away from you, just like this plot. Okay. So with this data, the argument was that the universe was expanding, which was huge news. And I'll come back to that towards the end of the talk. Okay. Next part of the story is that these gentlemen, Penzias and Wilson, in 1965, they discovered that if you look anywhere on the sky's glowing. And it's not glowing in visible light, it's glowing in very long wavelength radio waves. And this was really surprising that everywhere you look on the sky, it apparently has this glow to it. And in fact, if you look more closely at this glow, you'll see that, of course, the spectrum, meaning the brightness versus frequency, which I'm plotting here, this is brightness versus frequency, you'll find it has a characteristic shape, brightness versus frequency. And this is what's known to physicists as a black body spectrum. Okay, and that is, so for example, if you took a piece of coal and you heated it up to a few thousand degrees and you measured the spectrum, you would find that it has a spectrum that looks just like that. So any body that's in thermal equilibrium, that meaning it's all at one temperature, will have a characteristic spectrum that looks like that. So we know that about a lump of coal, but what's really surprising is that if you look out in the sky, the entire universe seems to have this one temperature, and turns out it is 2.725 Kelvin. I should say that this was measured with the COBE satellite, and these error bars have been blown up by a factor of 400. So this is a magnificent experiment where this is the best measured black body that's ever been looked at. Okay, so the really funny thing about this is that if you look on that side of the sky over there, it's 2.725 Kelvin. If you look at that part of the sky, it's 2.725 Kelvin. And those two ends of the universe that you can look at if you look that way and that way, they haven't talked to each other in billions of years. Okay? Yet they're at the same temperature. So something's going on there. The analogy I like is that it's as if a package shows up on your doorstep one day, and you open it up, and inside there's a chocolate chip cookie. You say, "Ooh, someone sent me a chocolate chip cookie," and inside the cookie, someone has put a very precise thermometer, and you find that the cookie temperature is 105.0000 degrees Fahrenheit. You say, "Huh, that's unusual," but you eat the cookie and you don't think more about it. But you go to your neighbors and they say, "Hey, did you get a cookie?" "I got a cookie." And you say, "Yes, it was a very good cookie." And they say, well, the funny thing was 105.000 Fahrenheit. You say, "Huh, that's unusual." And then so you find that everyone in your city got that cookie, everyone in the country, in fact, everyone in the world got a cookie just like that. And so you know, being a scientific thinker, you think, maybe those all came, the fact that they're all exactly the same temperature, maybe they all came from one oven, in one baking session, and they were sent out to everyone at the same time, and we all got our cookies the exact same temperature. And the universe is exactly that way. The fact that you look anywhere on the sky, and that right now the two ends of the universe have not talked to each other in billions of years means that it likely was that there was one cosmological oven, and that cosmological oven was all at one temperature, and that the ends of the universe you see out there are all the cosmological cookies that are all at the same temperature. Okay. So that is consistent exactly with this idea of a Big Bang, that the universe started out as a small hot object, and that now we're seeing it as much larger and cooled off all the way down to 2.7 Kelvin, but all at one temperature. Now, let me pause my story. My main story today is about that radiation, that glow, which is called the cosmic-microwave background. But let me pause in that story for a second to tell you a very important fact about the cosmic-microwave background radiation, but what happens afterwards. and that can be given by this cartoon here. That this is, I always like showing this because this is, in one page, I can give you the entire history of the universe. And as I said, we believe the universe started out with a Big Bang. And right after the Big Bang, due to quantum mechanics, the universe can't have been completely smooth. Quantum mechanics tells you that energy levels are discrete, and when you work out the math, it couldn't have been that you had a completely smooth universe. Shortly after the Big Bang, we believe an event occurred, which is called inflation, where the entire universe exponentially grew, very rapidly grew, and grew so fast, in fact, it actually grew faster than the speed of light. And that's okay if the entire fabric of space grows. Then about 300,000 years after the Big Bang, the universe is cooling this entire time. And after 300,000 years, the universe is cooled enough that you can form neutral hydrogen atoms. Before that, you couldn't. It was so hot you couldn't even form neutral hydrogen. Even earlier, you couldn't even form the nuclei that make up atoms. They were broken up into quarks. But at this time, 300,000 years, it's cooled enough that you form neutral hydrogen. And during all this time, there was light bouncing around like a ball in a pinball machine with the ionized hydrogen. But when the universe is cooled enough that hydrogen can form, this light doesn't bounce around anymore, and it's free to stream all the way, in fact, across time to be picked up by telescopes here on Earth. So these microwave background photons, this light from the very early universe, was emitted at 300,000 years after the Big Bang, and you have to come all the way forward to about 15, in fact, we now know it's closer to 14 billion years after the Big Bang, where we received this light in telescopes here on Earth. Okay, so really, because this light has come all the way from 300,000 years after the Big Bang, people like to say that that's a baby picture of the universe, that we're looking back all the way to the beginning of time, essentially, and we have a picture of what was going on there. And what we see is, as I'll show you more in a little bit, that the time of 300,000 years, the universe was fairly uniform, quite uniform, in fact, but at the level of parts per million, there were fluctuations there. And these come from the quantum fluctuations even earlier. Now, why are these fluctuations important? Well, these fluctuations are important because those tiny fluctuations, parts per million, they grow via gravity into all the structure that you see when you look out at night sky. When you look out, if you go camping and you're in a very dark place, look out in the sky, you see stars, and you see the whole Milky Way structure. If you brought a telescope with you, you'd look out and you'd see galaxies. And if your telescope was really good, you would see clusters of galaxies where galaxies are brought together. And further out, you see lots and lots of structure in the universe. And that's what our telescopes are showing us. And this is a little cartoon kind of view where you see the galaxies painted on the sky. And you can see in this little cartoon there's lots of structure. Well, all that structure grew from these small fluctuations that are shown from the cosmic microwave background, and they're grown via gravity to all the structure you see today. So these tiny fluctuations are essential to our model of the universe because those represent the fluctuations that grow into everything you see out on the night sky. Okay. And now, as I said, I'm going to pause my story to tell you a little bit about how that structure grew. And I'll do that. Here's a movie, and it's a computer simulation. What people do is they make a cube, and they put matter in that cube, and the matter in the cube is very uniform in density, but there are little seed structures in there. And those seed structures are the ones I just talked about in the cosmic microwave background. And when I start this movie, what you'll see is how in the computer simulation, structures grow. Okay, their little seeds are growing. Gravity pulls objects toward any overdensity. So any place that's a little bit more dense will start a collapse, a runaway collapse, where all the matter ends up at that slightly more dense place. And I really like this movie, so let me show it to you again. Right back up here and show you again. You see just a little seeding of structure grows into all these structures of galaxies on the sky. And these simulations are actually getting better and better. They really are starting to look like what we see out in the sky. Now, I want to show you this other movie. And this is, the movie I showed you is quite a large chunk of the universe. This movie is a little bit different. It's showing you the local universe. And let's start out with, there's our sun right there. But now you're moving away. And this is real data, but turned into an animation where you paint on galaxies where all the known galaxies are. And so that's our Milky Way. We have seen this animation from far away, but now you're backing away, and now you're starting to see other galaxies. So early on you saw the stars in our Milky Way, but now you're starting to see other galaxies, and this would be as if you were traveling. And you see there are different types. There are spiral galaxies, there are elliptical galaxies. And all this data was taken with an experiment called the Sloan Digital Sky Survey, which was in Apache Point, New Mexico, and has been watching the sky for years, just cataloging all these galaxies. It doesn't measure the entire sky, so what you're going to see is that the structure measured is in sheets. The universe actually isn't in sheets, but this is the way the survey was done. So there are all those galaxies. And now you can start to see these structures. And these structures here are on tens of what are called megaparsecs. A parsec is fairly close to a light year. So now you can see in these sheets, you can see all the structures, and you can see it looks a little bit like a foamy structure, like foam you'd see on the ocean as you're walking on the beach and looking at the spray. Okay, now we're going even further out, and these aren't galaxies. Now these are what are called quasars. These are very bright objects that we believe have black holes at the center of them, and they're so bright we can see them very far away. And so what they've done is they've painted on the cosmic microwave background, showing how far away it is, because as you go back in time, you're also going further away, given how light propagates. And so you see the local universe and then the far away. So let me stop there. Okay, so let me get back to my main story, which is the CMB fluctuations. And I'll show you this cartoon again. I'll keep coming back to this cartoon. Here you see, again, as I said, this baby picture of the universe. And so how big are those fluctuations that you see in the map? And the answer is they're very, very small. They're about 10 parts per million. And so given that the temperature of the universe, I told you, is about 2.7 Kelvin, we're looking for 20 to 100 microkelvin in fluctuations. So how big is that? So an analogy is if you compare those fluctuations to the average temperature, it's like the biggest redwood tree that you'd see in a park compared to the entire diameter of the Earth. And so when you want to measure these tiny fluctuations, you have to keep in mind that that's the scale that we're looking for. And another fact to tell you how hard this is if you ask all the power you detect from the cosmic microwave background in all the telescopes on the Earth that were looking for it, that couldn't heat one drop of water by 1 degree. So that's the kind of signal we're looking for out on the sky. So how do you, given that that's so hard, how do you do that? Well, we're going to employ a kind of detector called a bolometer, and it's really actually an old technology coming from the 50s. Langley invented the bolometer, which is really a sort of thermometer. It can measure the heat of a polar bear seat from a distance of 0.5 kilometer. And let me tell you, this actually isn't that hard an experiment. It's impressive. It's good for a limerick, but actually the amount of for a bolometer, modern day bolometer, this would be quite easy. But what's hard is measuring these tiny fluctuations. Now, how does a bolometer work? Well, what you do is you take an absorber for light, and you purposely isolate it from its surroundings, and you cool the surroundings very cold, because what you want to do is you want to reduce what's called thermal noise in the detector. Anything at a finite temperature has molecules that are jiggling around due to that temperature, and if you cool it down, those molecules quiet down, and you'll have a much more sensitive detector. Now, here's what bolometers actually look like. Here's a picture up in the corner. This is 1 millimeter per scale. So this is where light comes in, is picked up by an antenna, and then sensed by one of these, the antenna sends the signal to these bolometers over here that, as I said, are isolated. And these antennas are similar to the kind you'd have in your cell phone, for example, in picking up the radiation, but they're much more sensitive than your cell phone. And one of these pixels is in this array here, this array of hundreds of detectors. And there's in total 1,000 of these sensors or these bolometers on this array. Now this array is made from a silicon wafer. It's made by the same kind of techniques that you make a chip inside your phone or inside your computer, for example, a Pentium chip. And as I'll talk about in a sec, these are made on campus by graduate students here in the department. And so in fact, this is one of the very interesting things that PhD students in my group are learning. And then one of these arrays goes into the overall, what we call a focal plane. And you can see the size scale is about as big as my hand, and this is about as big as a really large plate, to give you a feeling. Now, this is the lab here on campus. We have a new building called the Marvell. It's actually called the Nano Lab, Marvell Nano Lab. And in fact, I think there's some tours that you can go on for Cal Day if you look at your schedule. And as I said, this is made using the same kind of technique of optical lithography that you'd make, for example, a Pentium chip. Now, an interesting thing is, as I said, the work in my group is done by PhD students. So here's me and a few of my students. And for these experiments that are trying to make these very sensitive measurements, we have PhD students making the detectors. And one of the things that many people don't know about science research is that much of the research, and in fact, in universities, most of the research are done by people in their 20s. Okay, these are graduate students in physics departments and other science departments who are doing the work. So if you get educated in, for example, physics, and you go to graduate school, you will be at the forefront of whatever research you'd be doing right away as soon as you start doing that research. And I think that, as I said, it's something that people don't realize. They think that it's perhaps older, middle-aged scientists who are doing the work, but no, it's really people in their 20s who are pushing this research. So I'll talk about a few different experiments. There's been several different experiments. It's such an exciting field that many people are working on it. An experiment that I worked on is called Maxima. And Maxima was a telescope that you can't see the dish here, but there's a parabolic reflector here, and then a very sensitive camera that has these bolometer type detectors in it. And what's going on in this picture is that the telescope is attached to a helium balloon. Okay, just like a kid's helium balloon, except that this one's about 5 stories tall right now. And as it rises in the sky and the air gets less dense, it actually gets as large as a football field. And in fact, it's as large as a football field and floating very slowly in the sky. And I think these kind of balloons account for quite a number of UFO sightings. And if you've ever seen one of these, you would understand right away when the sun hits it just right. Looks just like a flying saucer. And in fact, if you've ever heard the name of Roswell, New Mexico, I'll let you know that that's very close to a balloon base. And I think some of the sightings that come from around there are from these balloons. So the balloon has a parachute attached to it. And so after the flight, there's an explosive bolt that gets fired. And then our telescope comes down back to the ground based on that parachute, hopefully safely. So during one night, we made a measurement of the sky. This is about 10 degrees by 10 degrees on the sky, so about that large an angle. And at the time, this was the most sensitive measurement of this size of the sky. And so these hot and cold spots that you see here, this is a little hotter, a little colder. These hot and cold spots are hot and cold spots from the very beginning of the universe. And each hot spot you see there represents a slightly hot spot from the very early universe. And that slightly hot spot is a slightly more dense region that's going to start attracting matter toward it and start making things like stars, galaxies, and clusters of galaxies. So here you are seeing an actual baby picture of the universe. Now, the other thing I should tell you is, if I told you this is 10 degrees by 10 degrees, so here, this is 1 degree, for example. If you look at this map, do you see that there's one scale that's sort of dominant in the map? You know, if you had to tell someone there's a scale in the map, what would you say it is? You know, a prominent scale. What would people say? Half a degree. Okay, very good. Half a degree. Okay, so I would agree with that. Half a degree, maybe a degree, something on that scale. So what we do is we take this map and we analyze its spectrum. And before I get there, let me tell you what we're looking for. What we're looking for here is we're looking for what the geometry of space is. And Einstein told us many things, but one of the things he told us is that space itself can be curved. And that's a revolutionary idea, that the actual fabric of space can be curved. And maybe you're familiar with this idea. You've probably seen that, heard people talk about black holes. And the way we think about black holes is you take a rubber sheet and you put a heavy ball in it. You know the rubber sheet curves. In fact, they have something like that at Lawrence Hall of Science. And that represents Einstein's idea of a heavy object curving space. Well, not only is space curved around a black hole, but the entire universe can be curved. And so it can have a geometry that's flat, or it can have a positive curvature that's represented like this cartoon, or negative curvature like this cartoon. And we all learned in school that if you take a triangle, that you add up the three angles and it adds up to 180 degrees. Well, it turns out that that doesn't have to be the case. That's only true in so-called Euclidean geometry, where space is flat. If space is positively curved, you can see here that if you add up these angles, it adds up to more than 180 degrees. So if Einstein's was right and the universe was curved, you might have to go back to school and relearn all your geometry, because this would all be changed. And similarly, you have less than 180 degrees here if it's curved. So with those little, with that measurement I just showed you, we're actually able to tell which of these cases, because we actually know how large those spots were way back in the early universe. And what happens is, because of the curvature of space, light travels along these kinds of triangles. And if we measure the angle of this triangle emitted from the early universe, we'll be able to tell which of these cases is true. Okay, so in other words, we have this, what you can call a standard ruler, meaning we know how big those spots were at the beginning of the universe. We measure the angle in the sky of those spots, just as you guys did just a second ago. And that represents, in the spatial spectrum, a peak. And we look at the angle of that peak. Okay, and it looks like this. This is the spectrum. So you're used to the spectrum of sound. Higher frequencies are at one end of the spectrum, lower frequencies are at the low end. But this is a spectrum of angles. So small angles are over here, big angles are over here, and about half a degree is, as was suggested, is about here, okay? And this is bigger or smaller. So if we could tell how big the spots were in that picture I just showed you, we could tell which of these three stories are true about the universe. And it turns out that that we measured it with exactly that map, and this is the power measured in microkelvin squared, and this is the angular scale in some fancy units called multipoles, but really, as this is about half a degree, this is about a tenth of a degree over here, and you can see we made a nice measurement. The line is the theory, and these little dots are experimental measurements with error bars, and you compare that to theory, and you find it's exactly consistent with that middle picture. So the good news is we're not going to all have to go back to grade school and learn geometry again. I bet you're relieved. You probably didn't even know that was a possibility. And we know that the universe has this flat geometry. Okay. So it turns out that that's one of the first things we learned from that kind of map, But there's many, many things to learn, and so this has been a subject of great interest among cosmologists. And in fact, before the experiment I worked on called Maxima, there was an experiment called COBE, which is a satellite which was taking data about 1990. And this is the kind of map it made. And this is a little unfair to COBE because it measured the entire sky. But this is just showing you the resolution it had. And you can see that it measured these temperature fluctuations. But it didn't have enough spatial resolution to measure the spots that I just showed you. So then we measured the spots here in between these two satellites. But then in about the year in the 2000s, this satellite called WMAP was launched, and it was able to measure those spots with more precision than we were able to with Maxima, but confirming what we saw. And then just a few years ago, the European Space Agency launched something called Planck that had even better resolution. So you see, we're improving as we go along here in our measurements. Now, the measurements of COBE, measuring those fluctuations for the very first time, was so important that it earned the Nobel Prize. And so I show here one of the two Nobel Prize winners, George Smoot, who's a professor here at Berkeley. And here's George in his very nice tuxedo holding up the Nobel Prize. This is every physicist's dream, to be standing there in Stockholm in a tuxedo holding the Nobel Prize. And if that isn't enough, when you win the Nobel Prize, many things happen to you. And for George, he was able to be on the television show, Are You Smarter Than a Fifth Grader? And in fact, he won, and he got $1 million. So that was great. And he actually got to be on this TV show called Big Bang Theory. And so there's George, along with the cast of the TV show Big Bang Theory. So for all the young people in the audience, you see all the good things that happen to you when you win a Nobel Prize. So study hard in school. This is a picture of the Planck satellite on the ground being built. And so you can see the mirror here. You can see the image of the photographer in the mirror. There's another mirror here that's pointed, that bends light back toward the focal plane. And here's the focal plane. So that's like the chip in your camera that's picking up the signals. Here's the way it looks like when it's taking data. It's just a cartoon, of course. But what it shows is, here it is spinning, and that's the way it scans the sky. So here it comes around. You can see the image of the focal plane, first mirror, second mirror that bounces the light like this. And as it spins, it's tracing out a map of the sky. Now, what this cartoon is going to show you is a little bit fanciful. It's going to show the experiment painting the fluctuations onto the sky. So, of course, it's not actually painting the fluctuations on, it's just measuring them. But this is showing you the scan pattern in which it measures the sky and the resulting fluctuations. And so this is, this satellite's still out there. It's nearly done with this mission, but here it is measuring in this animation the sky. Now you see the fluctuations up here. You wonder, well, what's this bright stuff here? That's the galaxy. The galaxy is very bright in these wavelengths that they're looking at. And that's not from the beginning of the universe. That's local. That's the Milky Way. But we can ignore that when we're making our cosmological inferences. And there it is stretched out into a 2D map. Okay. And these measurements are really groundbreaking. And whenever we make a real step in progress, you'll see it on the front page of newspapers. And here it is, front page of New York Times. You look, this is March 2013. So this just came out weeks ago. So here you are seeing these very new results. Okay, and again, now we can measure the spectrum. And you remember that this is power or temperature versus angular scale. Again, half degree is here. And now you can see that we're measuring a much broader range of scales. And not only do we measure one peak, but we measure many. And if you remember, the maximum measurements, our error bars were about this big. Okay? Now the error bars are so small, I can hardly see them on this plot here. And so this is WMAP and Planck is the two satellite measurements. ACT and SPT are two ground-based measurements that can measure out to smaller scales. And I worked on the SPT team measuring out these bumps out here. And there's a line in here, which is the theory, and you can see that there's just an exquisite match of theory and experiment. It almost looks like we know what we're doing here, right? That you can write down on a piece of paper how these fluctuations should look, and you go out and you measure them with a satellite, with ground-based experiments, and it's just right on the line, okay? So this is part of what I mean when I talk about the golden age of cosmology. We're really making huge progress in our detailed knowledge. So let me tell you that, okay, so that is up to today, in fact, up to a few weeks ago. But let me tell you about what I'm working on right now, and that's the next stage, which is measuring not the temperature fluctuations, but the polarized fluctuations. So I told you before, if you were able to look out in the sky, and let's say you had eyes that could sense microwaves, you would see that the whole sky is glowing. And then if you looked a little more carefully, maybe you'd have to put on your glasses, you see the very faint fluctuations on the sky. And those are those fluctuations I told you about that are the seeds of structure. But now, let's say you put on your polarized sunglasses and you look at the sky, and what you have to do is you have to look at the sky, then turn your head, and then look back again, and compare those two pictures, okay? And don't get yourself dizzy when you do this experiment, but if you did it really carefully, you would be able to see that there are polarized fluctuations out in the sky. And those polarized fluctuations are the next thing that we're exploring in this research. Now I'm going to go back to my cartoon and tell you that, again, we're going to go back and look at 300,000 years after the Big Bang, but this time we're on the hunt for polarized fluctuations on the sky. And why are those interesting? Okay, so let me tell you a little bit about some fundamental physics. One thing that you may know is that there are only, we believe, 4 forces in all of physics, in all the universe. We believe that there's only 4 forces. There is gravity, which you know about because it's holding you to your seat right now. If I were to go back behind the bench here and turn this big switch that I have just for lab demos that turns off gravity, you'd all start floating up toward the ceiling. But I won't do that. You know about electromagnetic forces. That is holding you together. All the atoms in your body are held together by electromagnetic forces. So you better hope that's going to keep working for the near term, at least. But less known is the strong force, which holds together the nuclei of atoms. They're holding together all the nucleons inside the nuclei of the atoms in your body. And finally, the weak force, which, as the name implies, is a very weak force that mediates some particular kinds of interactions, including the ones that scatter neutrinos. Okay, so you can observe these 4 forces, but if you go back in time, the universe gets hotter and hotter. Remember, I told you that the early universe is hot and dense, and hotter is equivalent to meaning higher energy. Okay, if you think of the molecules in your body or in any object, as you get hotter and hotter, the molecules are moving faster and faster, and that means higher and higher energy. And that's so if you go back in time and you go back to hotter temperatures, you're going back to higher energy densities. And it turns out, if you look at the very early universe, it's so hot that it represents energy scales that are higher than present-day high-energy particle physics accelerators are exploring. So the CERN accelerator is exploring equivalently, it's a 14 TeV, tera electron volts, but that's equivalent to temperatures around 10 to 15 Kelvin, and that's what you need to discover the Higgs particle that's recently been announced from CERN. But if you go back to the early universe, we can actually look at energy scales that are 10 orders of magnitude, or add 10 more zeros to the energy scale of what we can learn back there. So that's really exciting. If we could go back to this early time, we could see that 3 of the 4 forces are unified, which are so-called grand unified theory scales. And we might even see a hint from even hotter temperatures where all forces are unified. That's called the Planck scale, where the theory that would describe that would be the so-called theory of everything, a very modestly named theory. And that theory of everything, it could be a string theory. that you've all read about. So maybe if we can go back, we're learning about string theory and about how the theory of everything would describe the entire universe. Okay, so now you can see why we're so motivated to measure this. That's the good news. The bad news is it's really even a tinier signal. I talked about microkelvin a little while ago. Well, now we're on the hunt for nanokelvin, hundreds of nanokelvin. Okay, so we have to advance in our technology of detectors, and that's something that my group here at Berkeley works very hard on. This is an experiment that we're working with right now called the polar bear experiment, polarization of the background radiation, and it's sitting at 17,000 feet in Chile. And 17,000 feet, you're probably thinking, wow, that's pretty high. And you might be wondering, can people work up at 17,000 feet? Well, the air is half as dense as it is at sea level. It turns out you can work up there, but often we'll wear oxygen tanks on our back that shoots a little bit of oxygen into our noses. And here's a cast of characters. Really just want to show you a picture of the people working on the experiment. And for example, Yuji, who's in this picture, is sitting up here in the audience. And as I said, the people who are really doing this research are people in their 20s. Okay, most of the people in this group are young people in their 20s, and everything you see in our experiment, from the basic detectors, the design of the detectors, and these are really revolutionary detectors trying to measure these nanokelvin signals, to how you put those, how you design the optics, to how you scan the sky, how you analyze the data for these very faint fluctuations. That's a very subtle art, and that's one of the things that Yuji is an expert in. And so all these things are done by these young people in the group. Okay, so I'll show you a little whirlwind slide show of how we assembled the telescope recently. Here's our construction crew in Chile. And so here is where things were in June of 2011. Okay, and so you'll see how fast this got put together. And at first we just had a plowed site. Then we put concrete down, put the telescope on, and there IAMS right after the concrete was poured, and that triangle is where you mount the telescope. There's the telescope arriving at 7,000 feet lower, and it is in pieces and has to be driven up. And you can see how dry the site is. It's one of the driest deserts in the world in northern Chile. Here it is being driven up to the high site, and there's the first piece arriving, and there's one of the graduate students, Dave, who's from San Diego, and now we're putting another piece on there. This part rotates. This is a big bearing. This is a very big lazy Susan, basically, and the whole top of the telescope can turn. This is the part that holds one of the mirrors being assembled. This is the secondary mirror being installed, and that's that part's being put on the telescope. That's the primary mirror. This is one of the most expensive parts of the experiment. So I'm off to the side, nervously biting my nails, hoping they don't drop it. And luckily it didn't get dropped. It got installed nicely. And there you see this is our control room. And here's one of my graduate students here at Berkeley, Brian. And he's starting to look at the data coming in over the telescope. This is a picture taken a little later than other pictures. Here's the assembly of the camera. I told you that the detectors are cooled to a very low temperature, about 1/4 of a Kelvin, 1/4 above absolute zero. So in other words, minus 272 degrees Celsius. So very cold. And here we are assembling the focal plane. These are these bolometer detectors I told you about, and this is being assembled at the site. You can see here's one of these oxygen tubes so we can breathe a little bit better. Here is the structure being assembled into the telescope, and here we're wheeling out the camera, about to install it in the telescope, and it's only about 8 months later, the picture I showed you at the beginning. And here we are, less than a year later, ready for what we call first flight. All these kind of astronomical or astrophysical experiments, when they first start, they see their first photons coming through. It's called first flight. All auspicious time. And here you see the very first signals we could see. And these aren't fluctuations in the cosmic microwave background. Just to get going, we look at a planet, just a bright object in the sky. But here we are on the first day, seeing a planet in two of the polarized detectors. And so that was a very nice timing of the experiment. And so now we've been up for a year taking data. And here's a map of the sky. And this is about 5 degrees by 5 degrees. And this one is just a temperature map. And we call it preliminary because we're just making sure that it's done correctly. And we don't have our polarization maps yet. But this map, it would look roughly similar to this if you could see the polarized fluctuations on the sky. And this map is right now the deepest map or the most sensitive map of the cosmic microwave background ever done. Okay, this is about, you saw the Planck satellite, this is 10 times more sensitive, or you would need 100 years of the Planck satellite to see this level of detail. Okay, so there's, we're getting that rapid progress from the development of these detectors, for example, in my group. Okay, so that's where we are, and so stay tuned for looking back at the very early universe with these kinds of measurements, and perhaps seeing these really high energy scales where the forces unify, and we'd be able to see energy scales way beyond accelerators. So that's going to be really exciting. So let me tell you, I'm coming to the end here. The last chapter here is I want to talk about the dark side of the universe. And that is these things that dark matter and dark energy that we don't understand yet. So remember I told you that Einstein told us that space can be curved, and when space is curved, if you send light through space as curved, it'll bend. So go back to that rubber sheet analogy. If you have a black hole that's making a dent in the rubber sheet, as you send light past the black hole, it's just like rolling a marble on that sheet. And I think that's how the Lawrence Hall of Science demo goes. And what you'll find is that if it rolls not too far and not too close, it'll deflect, it'll bend. And that's called gravitational lensing. And it's called lensing because it actually does magnify objects that are behind the black hole or any massive object. And so here what you see is you're seeing a bunch of galaxies. These are foreground galaxies. But so they represent what's called a cluster of galaxies, where many galaxies are in one place. But then you see these funny shapes, these arc shapes. And those arc shapes are not they're not banana-shaped galaxies. There's no such thing out there in the universe that we know of. But what it is that's gravitational lensing. And that's called strong gravitational lensing. And what Einstein theory tells us is that a galaxy that's being lensed will turn into what's called an Einstein ring. It'll turn into a circle if the galaxy and the lens aren't perfectly aligned. The ring breaks up into arcs, and so these arcs are strong lensing gravitational arcs. And by looking at these arcs, we can weigh how much this galaxy cluster weighs. And what we find is if we take the number for how much it weighs, and we count up all the stars and galaxies inside the galaxy cluster, we find that we can't account for all the mass inside that galaxy cluster. In fact, most of the mass is not accounted for by the luminous matter, by the stars inside that galaxy cluster. So what's going on? Why is it that there's so much mass in there that we can't see? Well, so we think it's some kind of stuff which we're calling dark matter. And we don't know what it is, but we have to call it something, so we call it dark matter. And so how are we sure that there really is this stuff called dark matter? For example, couldn't it be that gravity doesn't work the way that we think it works? That's possible. We think that gravity is the so-called 1/r² force, meaning that as you move away from, say, the Earth, the force of gravity weakens by 1/the square of the distance. Okay, now maybe it's not 1/r² exactly. Maybe it's a little bit off of that. And so that explains why we can't account for this correctly for this gravitational lensing. Okay, but here's some evidence that that's not true, that there really is some stuff out there that is dark matter. And this is a picture of a particular galaxy cluster called the bullet cluster. And it's called the bullet because this thing was called the bullet. And what's happened is two galaxy clusters have collided. And so you see one cluster here and one cluster here. Now, this, the yellowy stuff is the normal stuff, the stars and galaxies. And you can see that they've collided, and in fact, they've gone past each other. They've, this one went through this one, and they've gone this far apart. Now, what's this stuff? This stuff is the gravitational lensing. And what's happened is, it's a measurement of gravitational lensing. So this is the dark matter. The dark matter doesn't show up bright like this, like the stars. It only shows up in gravitational lensing. So apparently, what's happened is the dark matter has moved further. Again, this one came from over here, and this one came from over here. But the dark matter has passed further along than the luminous matter. Now, why is that? It's because the luminous matter interacts very strongly. It collides. All those stars collide via gravity and other interactions, electromagnetic interactions, whereas the dark matter only interacts via gravity. And so it doesn't have the same kind of collision. It's free to move past, only being held back by gravity. Okay, so let me show you a simulation of this. This is a computer simulation. But here are two galaxies, clusters of galaxies. They're minding their own business, flying through space. But all of a sudden, just like two skaters in a skating rink who are in a collision course, oops, they find themselves about to hit. And here they are. And so the luminous matter is the brightly colored stuff. And you see it starts to hit, you see it hitting there, but it gets stuck because of all those collisions. But the dark matter can go past because it doesn't interact in the same way, and it only interacts via gravity, and it goes past. And so that really shows that, that it isn't just gravity, a lack of knowledge of the way gravity works that makes us think there's dark matter out there. There really is some stuff out there that appears to act act differently than normal matter. Okay. So on all scales means that you see gravity, dark matter, you see it in our galaxy, the Milky Way. You see it in clusters of galaxies. Any length scale you can think of in the universe to measure, you see this dark matter. So what is it? Is it failed stars, stars that just don't light up? Is it some kind of, is it gas? We know there's lots of hydrogen gas out there. Or is it some kind of exotic particle, such as a weakly interacting massive particle? We actually know it's not just stars and gas, because we know from our theory of the early universe, we know how much normal matter there is, and there isn't enough. And so people are motivated to look for these exotic particles. And in fact, an experiment going on at Berkeley, in addition to other institutions, called the Cryogenic Dark Matter Search Experiment, CDMS, is looking for these exotic particles. And here's a detector. It's made from a germanium crystal. This is about as big as my hand. And what's supposed to happen is a WIMP comes in, and it interacts with the germanium, and it leaves some energy there, which you sense on the surface. And just like the bolometers I talked about earlier, this is also cooled to very low temperatures, in fact, even colder than the bolometers from my group. And it's designed to look for these WIMP interactions. And so they have to put it, as I said, in a very cold region. They have to make it very clean so they don't get radioactive material in there. And they have to put it deep inside a mine so that cosmic rays don't cause interfering effects. And in fact, there's some lab tours of this lab today, so you can look for that on your Cal Day schedule. Finally, my last thing I'm going to talk about before I conclude is dark energy. And here, if you look out on the sky, you can see stars exploding, what are called supernova events. And people had the idea, well, wait a second, these supernova events, they're so bright, we can see them very far away. Perhaps some of these supernovae, in particular something called a type 1 supernova, maybe they have very roughly the same brightness no matter where they occur. And if that's true, we can use them as what people call a standard candle. A light source out there in the universe that has a brightness that we know. And if we know how bright it is, we can tell how far away it is. Okay, so if we know how far away it is, we can do the same experiment that Hubble did. How far away is something compared to how fast it's going, but we can do it on much more distant scale. So we can test the Hubble expansion out to much further distances than Hubble did. Now, here is a map of the sky, and you can see lots of stuff there. But if you take two pictures of the sky and subtract them, you'll find, wait a second, something happened, and what happened was a supernova explosion. So that's how you find the supernovae, and you measure their brightness, and you measure, that tells you how far away they are, and then you measure how fast they're going, and you can do that by their Doppler shift, and then you can make a plot like this, okay? Basically, in this case, how far they are is given by one of these axes, and so I'm showing brightness here. As I said, that tells you how far away it is. And then the Doppler shift tells you how fast it's going. And here's the redshift here. And you can then apply models, that's all these lines, for how bright something should have been versus how fast it's going, just like the Hubble diagram I showed before. And if the universe, as we thought a few decades ago, was expanding but decelerating in its expansion, you would see a curve like this red one. But when people went out to measure this, they found the universe is not decelerating, but as time goes on, it's actually accelerating. So it should have, theory told us a long time ago that the universe should be hitting the brakes and slowing down its expansion. But the big surprise is we found that, in fact, the universe is hitting the gas and the expansion is actually accelerating. Okay. And this is an observation that we see, but we don't know why it's happening. And again, if you don't understand something, you have to at least give it a name. So we're saying that that's being driven by dark energy. But we don't know what that dark energy stuff is. But we know, since the universe is accelerating, it was such a big discovery that, again, we have another Nobel Prize to a Berkeley professor, and this is Saul Perlmutter getting the Nobel Prize. And as I said, there are many things that happen to you, perks that you get when you win the Nobel Prize. And one of Saul's was that he gets a special parking spot called a Nobel Laureate parking spot. So when you walk on campus, you'll see certain parking spots that have NL on them. And that's the Nobel Laureate parking spot. And as all of you know, in Berkeley, having your own parking spot, a pretty good prize. Okay, so for dark energy, we expected expansion to slow down, but big surprise, it's appearing to accelerate, and we don't know what's driving it, but we're calling it dark energy. And Einstein actually basically predicted dark energy. In his equations, he had a constant called the cosmological constant that acts exactly like dark energy. And in fact, it's a very interesting historical story that Einstein had this constant in there, but along the way, he decided it wasn't a good idea. And he said, nope, I think I should take it out. But he may have been right. It may be that we do need something like a cosmological constant. Okay, so it brings me to my next to last slide, which is now to make a pie chart of all the energy density in the universe and all the normal stuff that we know of, atoms making stars and galaxies. They only make about 4% of the universe here. And dark matter makes up about 22%, so it's much bigger, a factor of about 4 or 5 larger than the regular matter. And dark energy is the biggest part of the pie. So you see that everything we know about in detail fits in this little pie wedge, and very embarrassingly, 95% of the universe, we don't know what it is. And so, well, I'll say that at least that's something for people in the audience for the young people in the audience to become physicists and figure out what that 95% of the universe is. Okay, so here's my last slide. It's the same slide that I showed you at the very beginning, but now you've seen all the details of the story. So indeed, we really do live in a golden age of cosmology. Everything I talked about happened in the 20th century. And in fact, most of what I talked about happened in the last 20 years. So we're really, just like the universe is accelerating in its expansion, our knowledge of the universe seems to be accelerating in how fast we're learning it. We have a lot of evidence now that the universe started in a hot, dense state, which we're calling the Big Bang. The universe is clearly expanding, and we're learning about the details of that expansion. In fact, we're learning that it's accelerating, but it's accelerating for a reason we just don't understand by something we're calling dark energy. Also, we see evidence for a lot of matter out there. We've been able to weigh how much matter there is, but we don't understand what this stuff is. We're calling it dark matter. And this is what I'm calling here a minor problem, which is that we don't understand 95% of the universe, this dark matter and dark energy. As I said, that's going to leave something for future generations to discover. Thank you very much for coming. The coal, and you heated it up to a few thousand degrees, and you measured the spectrum, you would find that it has a spectrum looks just like that. So any body that's in thermal equilibrium, that meaning it's all at one temperature, will have a characteristic spectrum that looks like that. So that's that. We know that about a lump of coal. But what's really surprising is that if you look out in the sky, the entire universe seems to have this one temperature. And turns out it is 2.725 Kelvin. I should say that this was measured with the COBE satellite. And these error bars have been blown up by a factor of 400. So this is a magnificent experiment where this is the best measured black body that's ever been looked at. Okay, so the really funny thing about this is that if you look on that side of the sky over there, it's 2.725 Kelvin. If you look at that part of the sky, it's 2.725 Kelvin. And those two ends of the universe that you can look at with, if you look that way and that way, they haven't talked to each other in billions of years. Okay? Yet they're at the same temperature. So something's going on there. The analogy I like is that it's as if a package shows up on your doorstep one day, and you open it up, and inside there's a chocolate chip cookie. You say, "Ooh, someone sent me a chocolate chip cookie," and inside the cookie, someone has put a very precise thermometer, and you find that the cookie temperature is 105.0000 degrees Fahrenheit. You say, "Huh, that's unusual," but you eat the cookie and you don't think more about it. But you go to your neighbors, and they say, "Okay, this one, from this point of view, every other galaxy is running away." And what you'll find is that as the balloon expands, the further away the galaxy is, the further away the dot is on the balloon, the faster it's going. Okay? So this happens. This is just 2D, but it works in 3 dimensions too. You can think of people like to talk about loaves of bread with raisins in them. Imagine you put a lot of yeast in it, and as it bakes, it gets bigger and bigger. And all the raisins similarly will run away from each other. And the further away the raisins are, the faster they'll be running away from you, just like this clock. Okay. So with this data, the argument was that the universe was expanding, which was huge news. And I'll come back to that towards the end of the talk. Okay. Next part of the story is that these gentlemen, Penzias and Wilson, in 1965, they discovered that if you look anywhere on the sky's glowing. And it's not glowing in visible light, it's glowing in very long wavelength radio waves. And this was really surprising that everywhere you look on the sky, it apparently has this glow to it. And in fact, if you look more closely at this glow, you'll see that, of course, the spectrum, meaning the brightness versus frequency, which I'm plotting here, this is brightness versus frequency, you'll find it has a characteristic shape, brightness versus frequency. And this is what's known to physicists as a black body spectrum. Okay, and that is, so for example, if you took a piece of, we find that the universe is expanding with time, getting bigger and bigger. We expected that expansion to slow down with time, but we've been surprised by the discovery that that expansion is in fact accelerating. We don't know why it's accelerating, but we are saying that is being driven by something called dark energy that we don't yet understand. We've discovered that most of the matter in the universe can't be seen. It's not in stars and the things that you see out in the sky. And so we've given that a name too, even though we don't understand it. We've called it dark matter. So this is a huge amount of progress, but we still have this minor problem that we don't understand about 95% of the stuff in the universe, and that is this dark matter and dark energy. And by 95%, I mean if you weigh how much energy there is in the universe, 95% of it is in this dark matter and dark energy that we don't understand. So let me begin at the very beginning, that the universe began with a bang. And what evidence do we have from this? Well, let's go back to 1927, where all cosmologists smoked pipes. And we'll hear about the story of Edwin Hubble, who, using this telescope here, the Mount Wilson 100-inch telescope, he started looking at this data here, which is he started measuring galaxies, asking how far away are the galaxies, and then asking, well, and how fast are those galaxies going? And we found it's very interesting that the further away the galaxy is, the faster. All right, we'll get going now. Welcome to the physics department. As you may know, the physics department engages in a very wide range of research. There are 45 active faculty here in these buildings. And the area that I work in particular is experimental cosmology. As you'll see, what we're doing is trying to learn about how the universe started and evolved, but by building experiments that we really build with our own hands and that we take out and measure things. Now, here is a one-slide summary of the entire talk. So if someone tonight asked you, hey, what did you see at Cal Day today? If you can remember what's on the slide, you'll remember my entire talk. And that is, starting here, that we live in a golden age of cosmology. In every physics field, in fact, in many endeavors, often there's a real golden time for progress. And I'll argue that right now, the last really 20 years, we are really learning a huge amount about cosmology. Next here is that in that golden age that we're in, we're starting to have a detailed model that is emerging of how the universe started and how it's evolved. That model starts with a big bang, where the galaxy's going. And that is consistent with an expanding universe. Now, why is that? Why do you get that? The further away a galaxy is, the faster it's moving. Well, I should say that to talk about how fast we're learning things, it was controversial just before then that there even were galaxies, meaning that, when you look out in the sky, you see the Milky Way, and you know that, now you know that that's our galaxy. You know that we live in a spiral galaxy. And everyone here knows that you look outside our galaxy and there are other galaxies. But even that was controversial back in the early 1900s. So when Edwin Hubble said, hey, not only are there galaxies, but when you look at how the ones that are further away are going faster, that was really a revolution in what we knew. All right, so let me get back to the question. Why should it be that the further away a galaxy is, the faster it's going in an expanding universe? And I've got my little toy universe here. And what it is, it's a balloon. And the galaxies are painted on this balloon. You can, if your eyes are good, you can see the galaxies. And this is a 2D model of our 3D universe. So just the surface. You just think of the surface as a good model for how the universe expands. And so what I'm going to do is I'm going to blow it up for you here. Okay, now if you put yourself on any one of the little galaxies on my little balloon here, and as the balloon expands, you ask, what's happening to all the other little galaxies on the surface of that balloon? Well, what you'll find is that every single galaxy is running away from you.